What makes distributed computing so challenging? Imagine systems spread across the globe, each part needing to work seamlessly with the others. When one link breaks, the whole chain can falter. Picture a row of dominoes, one falls, setting off a chain reaction. In distributed systems, understanding these complexities is key. Failures can stem from network issues, software bugs, or even human error. Think of it like a delicate dance, every step must be precise for the performance to succeed. Now, let's delve deeper into how these systems function and the potential pitfalls that can arise. Ever wondered what sets distributed systems apart from single computer systems? In a single computer setup, one machine manages everything with shared resources, clear timing, and straightforward failures. However, in a distributed system, multiple machines collaborate over a network, facing unpredictable delays, no shared clock, and complex failure scenarios. This shift from centralized to networked operations introduces a host of challenges we'll delve into today. From shared memory to network communication, the transition marks a significant shift in how systems operate, requiring coordination across multiple nodes and dealing with the uncertainties of distributed environments. Through this lens, we'll unpack the intricacies of distributed systems and the implications they hold for modern computing. And remember, while a single computer may offer simplicity, the distributed approach opens doors to scalability and resilience in the face of evolving technological landscapes. In a distributed system, the core challenge arises from the absence of a global clock. Each computer operates on its own time, leading to clock drift and a lack of universal synchronization. When Machine A sends a message at 3 p.m. on its clock, Machine B may receive it at 2:59 p.m., creating a time discrepancy that disrupts event ordering. This discrepancy makes timestamps unreliable for determining sequence. Coordinating actions becomes complex without a shared notion of now. Imagine trying to choreograph a dance without a shared beat. The absence of a universal clock in distributed systems necessitates innovative solutions for event sequencing and action coordination. Ever wonder why messages sent over a network can arrive at unpredictable times? Picture this: Computer A sends a request to Computer B, but as the message weaves through routers and cables, its arrival time becomes a mystery. The delay could be anywhere from milliseconds to seconds due to network congestion, distance, and routing complexities. This uncertainty makes it a challenge to pinpoint the order of events across machines. Imagine the chaos of rush hour traffic, but in data form. The next time you hit send, remember, the journey to the recipient might be longer than you think. Imagine a scenario: User A deletes a paragraph while User B edits it. Who acted first? The ordering problem arises without a shared clock. This challenge is widespread, affecting bank transactions, social media posts, distributed databases, and more. In the absence of a global clock, systems must devise innovative strategies to ensure a consistent view of event sequencing. From simultaneous document editing to financial transactions, the need for accurate event ordering is paramount. By tackling this challenge creatively, systems can overcome the constraints of time discrepancies. In the world of distributed systems, logical clocks offer a clever solution. Each event is assigned a number as every process maintains a counter that increments with each action. When sending a message, the current counter value is included. Upon receiving a message, the receiver updates its counter to the maximum of the existing counter and the received one, plus 1. This establishes a partial order where lower counter values precede higher ones, creating a logical timeline. Invented by Leslie Lamport, logical clocks provide a consistent event ordering, enabling distributed systems to reason about causality without synchronized physical clocks. Remember, it's not about real-time measurement but about creating a reliable event sequence. In the world of distributed systems, Chapter 2 introduces us to the CAP theorem, the choice between consistency, availability, and partition tolerance. Consistency ensures all nodes view the same data simultaneously, while availability guarantees responses even during node failures. And partition tolerance means the system functions despite network splits. But here's the catch: you can't have all three at once. When faced with a network partition, you must pick between consistency and availability. This pivotal decision shapes how we architect distributed systems. So, how do we navigate this fundamental trade-off? Let's dive in. Ever wondered how banking systems navigate the delicate balance between consistency and availability during network splits? Picture this: in the choose consistency approach, transactions are refused to maintain accurate balances post-recovery. Contrastingly, choose availability allows continued transactions, risking temporary inaccuracies until reconciliation. Most banks prioritize consistency for precise data, while social media opts for availability, favoring access over real-time accuracy. It's a strategic dance between precision and access, ensuring a seamless user experience in the digital realm. Ever wondered how different databases handle trade-offs in the real world? PostgreSQL sticks to consistency, rejecting writes during network issues to maintain integrity. On the flip side, Cassandra prioritizes availability, allowing writes even in partitions, resolving conflicts later. But wait, there's a hybrid approach. Modern systems like Spanner offer strong consistency most of the time, gracefully degrading in network crises. In a world where banking demands precision and social networks crave uninterrupted service, these database strategies play crucial roles. Consistency or availability? The choice matters. Why is achieving consensus among multiple computers so challenging in distributed systems? Machines can crash, networks can fail, and messages can be lost or arrive out of order. Despite these obstacles, all operational machines must agree on a single outcome. Whether electing a leader, finalizing a transaction, or determining the next system state, the problem of consensus is omnipresent. This fundamental challenge demands synchronization in a world of potential chaos. In the world of server systems, consensus is crucial. When the master server goes down, surviving servers must quickly agree on a new leader. In distributed transactions, all databases must unanimously commit or abort. And for data replication, replicas must synchronize their operations to maintain identical data copies. These instances highlight the critical need for agreement and coordination in complex systems. Whether it's electing a leader, committing a transaction, or replicating data, consensus is the linchpin that keeps everything running smoothly. Ever wondered how a network of nodes reaches a collective decision? It all starts with a proposal phase, where one node suggests a value to the others. Then, in the discussion phase, messages fly back and forth as nodes assess proposals and iron out any conflicts. Next comes the crucial voting phase, where a majority consensus is needed for progress. Once that majority is reached, the decision is locked in and shared with all nodes. Complex algorithms like Paxos and Raft orchestrate this dance, ensuring system integrity even in the face of failures. The key lesson? As long as a majority of nodes are operational, the system can move forward smoothly and uphold consistency. Remember, strength lies in unity. In the complex world of distributed systems, failures take on a whole new dimension. These systems encounter challenges that single machine setups never face. Understanding these failure modes is key to crafting robust distributed applications. So, what are the most common ways in which distributed systems can stumble and fall? From network outages to data corruption, the possibilities are vast. Imagine a delicate web of connections, any one of which could break at any moment. These vulnerabilities demand our attention and careful planning. Let's delve into the intricate world of failure modes in distributed systems. Ever wondered how nodes can fail within a network? Let's explore 3 types of node failures. First up, we have the crash failure, a straightforward scenario where a node abruptly stops working, akin to a computer suddenly powering off. This type is easily detectable, with a clean failure mode and no erroneous data transmission. Next, the omission failure occurs when a node selectively misses certain messages, making detection trickier as it can resemble a sluggish network, resulting in partial communication. Lastly, the Byzantine failure presents the most challenging situation, where a node acts erratically, sending deceitful or harmful data. Detecting this type is highly complex, requiring specialized protocols for handling. Remember, different failures demand different approaches. In the world of networks, a silent threat looms: network partitions. Imagine a scenario where the network fractures, rendering communication impossible between its divided segments. Each side, unaware of the other's existence, carries on independently. Decisions clash, updates diverge, and leaders differ. When the partition mends, chaos ensues as conflicting states collide. The CAP theorem comes into focus, presenting a stark dilemma: maintain consistency by halting updates or risk divergence by forging ahead. In the face of network partitions, tough choices must be made. Take heed, the silent killer demands our attention. Ever wondered what could go wrong in a distributed system? Let's dive into some common failure scenarios. Split brain: picture this: two nodes both claiming to be the leader, causing conflicting data that needs to be sorted out later. Cascading failures: it all starts with one node crashing, which then overwhelms the remaining nodes, leading to a chain reaction of crashes. Lost updates: imagine a scenario where a write is acknowledged but then disappears before being replicated, leaving the client with a false sense of security. Deadlock: nodes stuck in a cycle of waiting for each other, like a game of musical chairs with no winners. In distributed systems, these failure scenarios can wreak havoc if not handled properly. Remember, in the world of distributed systems, even the smallest glitch can have far-reaching consequences. In the ever-evolving landscape of system resilience, key strategies stand out. Replication spreads data across nodes, ensuring seamless handover if one falters. Yet, the sync dance of replicas demands constant vigilance. Timeouts and retries play a crucial role, setting sensible limits and retrying failed ops prevent bottlenecks. But tread lightly, for overzealous retries can compound issues under strain. Health checks act as sentinels, swiftly detecting and sidelining malfunctioning nodes. Graceful degradation shines in adversity, offering a lifeline of reduced but steady service when parts falter. In this intricate dance of system fortitude, adaptability is king, ensuring continuity even when faced with disruption. Distributed systems pose unique challenges: no shared clock, network failures, and intricate failure modes. These aren't just engineering hurdles, they're proven limitations, like the CAP theorem. Successful systems navigate by choosing consistency models, using consensus protocols, handling failures gracefully, and adapting to unreliable networks. In this complex web of trade-offs, careful design is crucial. So, how do we tackle these intricate systems to ensure they function seamlessly? By making strategic choices, implementing robust protocols, and embracing the reality of asynchronous communication. It's all about balance, adaptability, and resilience in the face of uncertainty. Ever feel like time is playing tricks on you? In distributed systems, time and ordering are complex puzzles without a global clock. To unravel event sequences, we rely on logical clocks or consensus protocols. The CAP theorem reminds us of tough choices during network partitions: consistency or availability, not both. Consensus, achieved through meticulous protocols like Paxos or Raft, is the key to harmonizing distributed nodes. With various failure scenarios lurking, node crashes, network splits, or Byzantine mishaps, we must design for resilience. Anticipate failures, fortify with replication, timeouts, and graceful degradation. Prepare for the worst, and your system will thrive. Question 1. Why can't we rely on timestamps alone in a distributed system? Each machine has its clock, leading to drifting time and no shared now across the system. A social media platform prioritizes availability and partition tolerance (AP) by allowing posts during server unavailability, trading temporary inconsistency. Consensus is crucial in distributed systems for shared decision-making amidst failures and delays. Byzantine failures are the toughest to handle due to arbitrary node behavior and incorrect data transmission, demanding intricate detection and recovery protocols. In distributed systems, navigating time, partitions, and failures requires strategic design and resilient protocols for seamless operation.